Okay, so here we're going to consider a situation of applying Gauss's law to a case where we have cylindrical symmetry. And we're going to consider that we have a long cylinder which carries a charge density that is proportional to the distance away from the axis. So it's given by rho is equal to Ks, where K is some constant. And we want to find the electric field inside the cylinder. So the first thing we're going to do is we're going to draw our Gaussian surface inside, and our Gaussian surface is going to have a radius which is given by A and has a length which is given by L. And this is situated along the axis of our cylinder. So the next thing that we want to do is we're going to write down Gauss's law. So for Gauss's law, we have our integral for electric surface integral electric field dA is equal to the total charge enclosed divided by epsilon naught. Okay, so what we want to do is what is the total charge which is enclosed by our cylindrical Gaussian surface? So what we know is the total charge enclosed can be obtained by integrating the charge density rho over the volume. Okay, so here we have our volume integral of rho d tau. And d tau for a cylindrical coordinate system is given by S ds d phi dz. Okay, so let's write this out in a little bit of detail. So we have the total charge enclosed will be equal to a triple integral. For z, it's going to be between 0 and L. For phi, it's between 0 and 2 pi. And for s, it's between 0 and a. Rho is equal to Ks, and we have S ds d phi dz. So now we do this integral. Integrate with respect to z, we're going to get L. Integrate with respect to phi, we're going to get 2 pi. And integrate with respect to s, we're going to have s cubed over 3. Okay, so just follow on with this integral. What we have is total charge enclosed will be equal to 2 pi Lk, so 2 pi k by a cubed all over 3. Okay, so if we go back to Gauss's law now, we have our surface integral of E dot dA. Again, since we have symmetry, the electric field is pointing outwards from the surface, and it's uniform over the surface. The electric field can be taken outside the bracket, so we have magnitude of the electric field by the integral of dA, which will give us 2 pi AL times the electric field. Okay. So now we know that this is going to be equal to Q, the total charge enclosed, divided by epsilon naught. So therefore we can write the 2 over 3 pi L K A cubed. And what we get is our electric field will be equal to 1 over 3 Ka squared. And it's in the s hat direction. Now, of course, since the electric field is perpendicular to the infinitesimal surface area element dA, which is in the s hat direction, the two ends of a cylinder are going to contribute nothing, so this is our final answer.